So here we're going to be examining an example of doing a one mean t-test. And note that in the previous example, we only focused on the confidence interval. So we did not even set up or need to set up a hypothesis. We just use some formulas and calculate the confidence interval that we could expect based on our sample data. Now let's think of an example here. Let's take a step back and think of an example of running. Think of it, uh, suppose you want to answer the question, is the typical US runner getting faster or slower over time? And we can think of it as in terms of US runner, or maybe cherry blossom runners would be best, because US runner, that's all the runners in the United States. So if you get a sample, you need to, for those independent conditions, we need to get a simple random sample of people in the entire United States. So if you just go to one city, it's not going to be independent. It's not going to work. So maybe your question is the typical cherry blossom race runner getting faster or slower over time? So the average time for all runners who finished the cherry blossom race in 2006 was 93.29 minutes, which is 93 minutes and about 17 seconds. So maybe your question is, last 10 years ago or 15 years ago, the average race time was to finish the race in 93.29 minutes. And maybe you want to know, well, has the average time increased or decreased? And once again, how are we going to do that? Well, we're going to get a sample of data. We got a sample of data, and we can then check that out. So suppose we got a sample of 100 runners from the cherry blossom race in 2017, and their finish timings, how much time it took for them to finish. That's what we're measuring. That's what we're measuring here. There's 93.29 minutes. Is the amount of time it take a person to finish. This is the average in 2006. Now we got the data for 2017, and then we actually created a histogram here for that information. Now, of course, what do we need to ask first? What do we ask first? There's two major questions: independence, and normality. Do those conditions, can those conditions be met? Independence, well, yes, we say yes. We random sampled 100 people from the race. It was a simple random sample, so it's independent. Great. Is the data normal? What can we do? Well, let's create a histogram. Create a histogram for the data. And does it look normal? Actually, it looks pretty darn normal. So the normality assumption seems to hold, definitely holds in the sample that we got. So we can assume it holds for the population, and we know this context. Other knowledge, previous knowledge, domain knowledge can come in hand here too, and help address these conditions. So normality assumption also seems to check well. And let's also take a look at the data. So this is about frequency, right? So most runners are between 100, a little bit less, and a little bit higher than 100, and then minutes, and so on. Because you can see less people take a long time, and less people take a lot. Less people are on the lower ends of the distribution, as is the case with the normal distribution. So let's go through the whole setup here. First, number one, really, we check the assumptions. Or maybe that's kind of like ground zero. Check the assumptions. So number one, set up the hypothesis test. The null hypothesis is that the average is 93 minutes. The population average is 93 minutes, 93.29. Now, you're going to test whether the mean changed, or better, significantly changed from that value. So the alternative hypothesis is that no, it's different. We don't really know if it's higher or lower. We want to test, and like I said before, it's always good to do a two-sided test unless you really know, things could only have gone one side. So you do a one-sided test. But if it could have gone two sides, we do a two-sided test. So step two, we find the t-score. That t-score measure that translates, but we don't do that first. That translates the value into standard deviations. But before that, we need the standard error. We need the standard error measure here, which is the standard deviation divided by the square root of the sample. I don't know if you remember this. Is this standard deviation, or we don't have the population? This is for population value, right? That symbol. So we just use little s. Ooh. We just use little s here for standard deviation of the sample, and n. So this is the square root of n. And it's 170. So that's the standard error is 170. Now we calculate the t-score, which is calculating our difference in terms of standard deviations. And that's our mean. So this is the X bar. We didn't show this before, but this is the X bar, the mean of the data. We have this data right here. We kind of show the data here, but this is from the sample of 2017. This is 2017 sample. It's 97.3, the average. Once again, you can see, 97.3, it's much higher than 93. So yes, it went up, but no, it's not enough. We want to know if this difference is significant, statistically significant. So we got the t-score, that's the third step. And it's just like when we did with the proportion for the z-score. And the t-score, we get the average value, the current sample, x mean, minus the assumed population value, the old mean that we had that we're comparing against, whatever mean that we're comparing against, and then divided by the standard error, the 170 here. And then we get this 2.37. And the 2.37 is the t-score, which is the t cutoff point. So, and so what do we do with this 2.37 value? Well, these calculations here, we can easily calculate the equation. It's fairly simple. But then to get the p-value corresponding with this number of standard deviations, we want to put it into a function like the pt function to find the p-value. So let's just read here what's going on. For degrees of freedom equals 100. So 100, the sample is 100, minus 1 is 99. We can determine using statistical software that the area under the t-distribution with 99 degrees of freedom that is above our observed t-score of 2.37 is 0.01, which we double to get the p-value 0.02, and we double because of the two-sided test. Because the p-value is small, the data provides strong evidence that the average run time for the cherry blossom run is different, statistically different than the average 2016 average. So let's go on to see what happened here. We get the 2.37 t-score number, and then the last step is to find the p-value, and we just plug it into the function, and the first number is the t-score, and then the degrees of freedom of the sample you have, and then you get a p-value, probability value. So note that this 2.30, where's this 2.37? So 2.37 is somewhere over here in the distribution, right? So what does this function pt give us? Well, it gives us the probability of getting this value or higher, this value or higher, this value or higher. And what is the probability of getting this value or higher? Well, if you just put it in, because it counts, the default of the pt function is to count from left to right and sum everything. The probability it's going to give you, if you put 2.37, is going to be 1 minus, is going to be it's going to be like 99. It's 1 minus 0.00986, which is 0.00 1 minus 0.0986, which is 99. Sorry, it's 99. 99.99. So the probability of getting this value or higher is going the p-value here that's going to give you is a 99 p-value. But that's not true. 99 is getting 2.37 or below. Okay? 99 is getting 2.37 or below. So this is why we need this one minus here, because what this PT function is counting this whole area over here. And actually what we want is this area over here only. So when and the standard rule for this is if your t-score is positive and you're putting it into the PT function, you need to subtract it from 1 to get the actual p-value the way we use it. So when you do that, you see that the probability of getting 2.37 or above is very low. It's a very low probability. Most values are below that. In that case, because the p-value is so small, we reject the null hypothesis, and we accept that there is a statistically significant difference from the 2017 compared to the 2006 average values. And that's pretty much we can say. We cannot say anything about cause. All we can say is that there's a statistically significant difference with p-value at 0.00986. And we could also calculate the confidence interval for this. We don't do it here, but we could also calculate the confidence interval for this measurement here, which we saw in the previous videos. Here's just an extra message to kind of remind you that by default, this function calculates the p-value from the lower end. So it calculates everything on the curve from left to right. And so when you just have a positive t-score like this one here, 2.37, the p-value is going to look really huge because it's going to give you everything of that value and less. And that's not what we want. We want to know of the probability of that value or higher, because we want to know just at that value itself, because we want to calculate just how far that value is. If you use the other number here, 99%, that includes all the other values. So it doesn't make sense. It doesn't make sense. All the average values are likely to happen. We know that the values very close to the average are likely to happen, but we want to know this value here or more extreme. So that's how we approach it. And then we would, if we wanted to double that, we would, if we do a two-sided test, we need to double this value, and then, but we still need to subtract from 1 first, and then double, which is what they did here. They did double, which was first we had 0.01 and then double to 0.02, which is very unlikely. It's below 95%, and it's enough to reject the null hypothesis. I hope this helped, and we next talk about the t-test based on a difference of 2 variables.